Hello friends, I welcome you in lecture number 12 on recurrence relations. In this lecture also we are going to solve one more non-homogeneous recurrence relation using method of undetermined coefficients. This question was asked in GTU Winter 2020 exam. We can observe that this term is not in this form, something into Aj, where Aj is a term of the sequence an, which is the solution of given recurrence relation. Because of presence of this term, which we will denote by function of n, this recurrence relation is non-homogeneous. Now, as we know, to solve the given non-homogeneous recurrence relation, we have to first consider the associated homogeneous recurrence relation, and we have to solve it first. So first we are writing given recurrence relation, given recurrence relation is a suffix n minus 4 times a n minus 1 plus 4 times a n minus 2 equal to n plus 3 to the power n, and we give this number 1. Now we write down the homogeneous recurrence relation associated with number 1. The associated, we are writing associated homogeneous recurrence relation or recurrence relation which is homogeneous and it is corresponding to a given recurrence relation. The associated homogeneous recurrence relation is, we will consider this term equal to 0 to write down the corresponding homogeneous recurrence relation, and plus 4 times a n minus 2 equal to 0. Now we solve this homogeneous recurrence relation. For that we take a n. We know that solution is always in this form if our recurrence relation is linear homogeneous with constant coefficients. So we take a n equal to r raised to n in number 2, and we have r raised to n minus 4 times a n is r raised to n, therefore a n minus 1 is r raised to n minus 1 plus 4 times a n minus 2 is r to the power n minus 2 equal to 0, and we divide this equation by lowest degree term in r. Here r raised to n minus 2 is the lowest degree term, so we divide each term of this equation, which is obtained by taking a n equal to r raised to n in equation 2 by r raised to n minus 2. So we can see if I divide r raised to n by r raised to n minus 2, I will have r raised to n minus n plus 2. So I will be left with r square. Similarly here I have r raised to n minus 1, and that I will divide by n minus 2. So I have n minus 1 minus n plus 2. N will cancel out and I am left with r. And here r raised to n minus 2 is divided by r raised to n minus 2, so we have 4 equal to 0, and this is the characteristic equation of homogeneous recurrence relation which we have given as number 2, and this is clearly square of r minus 2. R minus 2 square equal to 0, therefore we have r minus 2 times r minus 2 equal to 0, therefore r equal to 2 comma 2. So we have equal and real roots. The roots of characteristic equation are real and equal, and therefore the general solution of homogeneous recurrence relation, the general solution of number 2, which is homogeneous recurrence relation, will be alpha 1 times 2 raised to n plus alpha 2 times 2 raised to n, and to make these two independent we will multiply by n, and general solution of homogeneous recurrence relation is denoted by an, and here we write h in the bracket and we give this number 3. Now we have to find out the particular solution of non-homogeneous recurrence relation, which we have denoted by 1. So first we have to assume the form of particular solution, and that form we will decide using this function. So this function is denoted by f of n, which is n plus 3 raised to n. Now f of n is n plus 3 raised to n. Now whenever we have two functions in the addition, we will decide the choice corresponding to each of the two functions in the addition, and then we will add those two choices. So corresponding to this function n, first we write this function n in this form, n times 1 raised to n. As we know that whenever we want to find out particular solution, we have to assume our function in this form, polynomial in n into nth power of some constant. Here I have n only, so I am writing s equal to 1. So corresponding to this this function n, I have s equal to 1, and s equal to 1 is not the root of characteristic equation. Roots of characteristic equation are 2 repeated 2 times. So therefore the choice corresponding to this function n is here this is polynomial of first degree, so I will write p0 plus p1 n, and I keep 1 raised to n as it is because s equal to 1 is not the root of characteristic equation. Therefore I will have p0 plus p1n corresponding to this function n. So that we write here p0 plus p1n is the part of a particular solution corresponding to this function n. Similarly, we have to decide the trial solution corresponding to 3 raised to n. So now I will write 3 raised to n in this form. So if we compare with polynomial in n into s raised to n, then we can see here I have 3 raised to n, it is in this form, so we can assume here 1. That is, we have constant polynomial into s raised to n where s is equal to 3, and we check whether s equal to 3 is a root of characteristic equation or not. So obviously not, s equal to 3 is not a root of characteristic equation. So corresponding to this part, our choice will be this is 1, that is polynomial of degree 0 or constant polynomial. So corresponding to 1, I will assume some arbitrary constant, say p2, p0 and p1 are used here, and I will keep 3 raised to n as it is. Therefore the trial solution corresponding to 3 raised to n is p2 times 3 raised to n, and we have to add those two solutions corresponding to n and 3 raised to n for the choice corresponding to n plus 3 raised to n. So in this way we can decide that what will be the type of particular solution, or our particular solution is in which form. So whenever you have two functions of n in the addition, then you decide the choices for each of the two functions in the addition, and then you add corresponding choices. So here we assume that particular solution is in this form. Assume that the particular solution of given non-homogeneous recurrence relation, which we have given number 1, is a n p equal to p0 plus p1n, that corresponds to this function, plus p2 times 3 raised to n, that corresponds to 3 raised to n. Now once we decide correct choice for particular solution, then we have to substitute this solution in the given non-homogeneous recurrence relation. We assume that this A and P is a solution of given non-homogeneous recurrence relation, therefore it must satisfy the given non-homogeneous recurrence relation. So we can write that since A and P is a solution of equation number 1, which is given recurrence relation, we substitute A and P in place of An. So here I will consider A and P, then 4An minus 1P plus 4An minus 2P equal to n plus 3 raised to n. So we have A and P minus 4 into An minus 1P plus 4 into An minus 2P equal to n plus 3 raised to n. Now we have A and P equal to P0 plus P1n plus P2 times 3 raised to n minus 4 times An minus 1P. So we replace n by n minus 1 everywhere in A and P. P0 plus P1 into n minus 1 plus P2 into 3 raised to n minus 1 and plus 4 times An minus 2. So we replace n by n minus 2 and we have P0 plus P1 into n minus 2 plus P2 into 3 raised to n minus 2 equal to n plus 3 raised to n plus 3 raised to n. And remember, we want to determine these values of P0, P1 and P2, and on the right hand side we have n plus 3 raised to n. So we will convert our left hand side in this form: polynomial of degree 1 in n plus 3 raised to n. So therefore let me rearrange or rewrite some terms so that I can convert my left hand side in this form, and then I can compare the coefficients of equal powers of n and 3 raised to n. And this is let me write one more step. Here I have P0 plus P1 into n minus P1 P2 into this I can rewrite as 3 raised to n into 3 raised to minus 1. And let me rewrite this bracket also. It is P0 plus P1 into n minus 2P1, and this I rewrite as 3 raised to n into 3 raised to minus 2 equal to n plus 3 raised to n. Therefore now we expand these brackets: P0 plus P1 into n plus P2 into 3 raised to n and minus 4 times P0 minus 4 times P1n and minus minus plus 4 times P1, and here I have P2 3 raised to n divided by 3, and due to minus sign I have 4 P2 3 raised to n divided by 3. I am multiplying this bracket by minus 4 and I have minus 4P0 minus 4P1n plus 4P1 minus 4P2 3 raised to n into 3 raised to minus 1, which is 1 by 3. Similarly, let me simplify this also. I multiply with 4 each term of the bracket. 4 times P0 plus 4 times P1n minus 8 times P1 plus 4 times P2 3 raised to n into 3 raised to minus 2, which is 1 over 3 square, which is 9, equal to n plus 3 raised to n. Okay, fine. Now we have to collect the coefficients of n and 3 raised to n on left hand side, as well as we have to combine the constant term. So here we can see this 4p0 will get cancelled, 4p0 minus 4p0, and here I have 4p1 minus 8p1, that is going to be minus 4p1, and this is also constant. So constant term is p0 minus 4 times p1. Now we have to collect the coefficient of n, and you can see this also will get cancelled, 4p1n minus 4p1n. So there is only one term with coefficient of n, and it is p1 times n. Now we collect all those terms in which we have 3 raised to n. So those terms are p2 into 3 raised to n, and this is also containing p2 into 3 raised to n, and this one. In each of these terms we have p2 into 3 raised to n common. So let me take p2 into 3 raised to n common, and here I am left with 1. Here I am left with minus 4 by 3, and here 4 by 9, p2 times 3 raised to n equal to, this we can rewrite as 0 plus 1 into n plus 1 into 3 raised to n. And now we can compare both sides. On left hand side, constant term is p0 minus 4 times p1. Here constant term is 0, so this is equal to 0, and here coefficient of n is p1, and here coefficient of n is 1, therefore p1 is 1. And once we obtain p1, we can obtain p0 from here. p0 is 4p1 and p1 is 1, therefore p0 is 4. And this is the coefficient of 3 raised to n. 1 minus 4 by 3 plus 4 by 9. We will simplify this. 1 minus 4 by 3 plus 4 by 9 times p2, which is coefficient of 3 raised to n on left hand side. Here coefficient of 3 raised to n is 1. And if I simplify this, I have to multiply by 9, or I take LCM first, and I have 9 minus 12 plus 4 times p2 equal to 1, and therefore this is 9 plus 4, 13 minus 12, that is 1, and we take right hand 9 on right hand side, so we have p2 equal to 9, and p0 is 4 and p1 is 1. So this is what we required. We required the undetermined coefficients in our choice of particular solution. So here we will substitute values of p0, p1 and p2. So that will be the particular solution. Therefore, the particular solution of given non-homogeneous recurrence relation 1 is A and P equal to P0 plus P1n. P0 is 4 and P1 is 1. That is 4 plus 1 into n, and P2 is 9. That is 9 times 3 raised to n. And if we wish, we can rewrite this as, we can write 9 as 3 square, and we can combine with this 4 plus n plus 3 raised to n plus 2. Now once we obtain particular solution and ANH, that is solution of homogeneous recurrence relation, we can write down the general solution of given recurrence relation. General solution of given recurrence relation, that is denoted by 1, is AN equal to addition of ANH and ANP. Our ANH was alpha 1 into 2 raised to n plus alpha 2 into 2 raised to n into n. Because of repeated roots, we multiplied by n, and our particular solution is 4 plus n plus 3 raised to n plus 2, and this I can rewrite as alpha 1 plus alpha 2 n times 2 raised to n plus 4 plus n plus 3 raised to n plus 2. This is the required solution of given non-homogeneous recurrence relation, and here n takes the values 0, 1, 2 and so on, and this alpha 1 and alpha 2 are arbitrary constants, and this method is called method of undetermined coefficients, and it is very easy. You just have to keep in mind that your particular solution must be selected correctly. If your particular solution is not selected properly, then you will get wrong answer.